Hello, everybody. Welcome to the August 2008 Prelim Problem 3. Now, this is a pretty old prelim, and the material has shifted a little since then, so we really haven't seen very much of what we need for this problem, which is the multivariate normal distribution. But we've certainly seen best and most powerful tests, and let's see what we can do. In this problem, we have x1, x2, and x3 IID, or a random sample, from the normal distribution with mean mu and variance 1. And then we have y1, y2, y3 IID from the normal 0, 1 distribution. And we are given that these two random samples are independent. And then we define new random variables, W1, W2, and W3. So Wi as xi plus yi, and this is defined for I equals 1, 2, and 3. And then we're also defining a W4, which makes this problem a little bit tricky. So W4 is x1 plus x2. And the reason I say it makes this a little bit tricky is because the W's are no longer IID. They are actually neither I in IID. They're not identically distributed, and they're not independent. So we have a known fixed given constant mu1 greater than 0. And in part A, we want to find the best or most powerful test of size alpha for testing mu equals 0 versus mu equals mu1. And in part A, we want to do it only based on observing W1, W2, and W3. So this part should be relatively easy because we don't have the dependence of W4. To find the best or most powerful test in the simple versus simple case, we want to use the Neiman-Pearson lemma. Here we want to form a likelihood ratio. So we need the joint PDF for the three W's, and they are IID. They're clearly independent because W1 is x1 plus y1 and W2 is x2 plus y2, et cetera. And those are independent, all the x's and all the y's and the x's and the y's. So what we have is W1, W2, W3. These are IID, and they're just simple linear combinations of normals. So they're normal again. And if you look at, say, the mean for W1 or WI, this is the mean for x1 plus y1. And you can run the expectation across. And the mean for x1 is mu, and for y, it's 0. So we get mean mu, and we get that in the case for Wi, I equals 1, 2, or 3. And then the variance for W1, this is the variance for x1 plus y1. And in general, variances do not distribute across sums, but they do if the random variables are independent. So this is the variance of x1 plus the variance of y1. And both of these distributions had variance 1. So we get that W1, W2, W3, they all have a variance of 2. Okay, so we can write down the joint PDF for W1, W2, and W3. Again, they're independent, so we just need to multiply 3 normal PDFs. So I've got the joint PDF for W1, W2, W3. It's going to be a function of the unknown parameter. Just to be clear, because this changes in part B, this vector W is W1, W2, and W3. And so we get 2 pi sigma squared being 2. So let me multiply it in there already. We get 4 pi minus 3 over 2. So that's in place of what you usually see for the normal as the minus n over 2, because n is 3 here. And then we get e to the minus 1 over 2 sigma squared, which is 4. And the sum, as I goes from 1 to 3, of Wi minus mu squared. So with that, we're ready to form the likelihood ratio. I have been calling this, if you took a class with me, I've been calling it lambda, and you can call it whatever you want or call it nothing. You can write the likelihood ratio is and just write it down. But I usually have the null hypothesis parameter, which is mu equals 0, and then the alternate hypothesis parameter, which is mu equals mu1. And this is made up of the joint PDF with the null hypothesis parameter over the joint PDF with the alternate hypothesis parameter. And we've got that distribution up here. So when we form this ratio, this term is going to cancel and we'll be left with e to the minus 1/4 sum of the wi squared minus the sum of the wi minus mu1 squared. And both of these sums go from 1 to 3. So Neiman and Pearson, they say this is the statistic on which we want to base the test. And part of the Neiman Pearson lemma says to reject if this is below some k. So this is like the rejection rule. And the next step is always to kind of simplify this and try to isolate the w's on one side of this inequality. So one thing I can do is take the log of both sides, and that will leave us with minus 1/4. While I'm here, I'm going to square this and run the sum through. So this is the sum of wi squared minus 2 mu1 sum wi plus 3 mu1 squared. So that's like your n mu1 squared, but n is 3. So we've run the sum through. I goes from 1 to 3. And this is less than or equal to some k1. And you do not need to do this. I'm just going to do it one time. This is the log of k. But as I'm sure you know, we don't need to keep track of these constants. It just depends on how we want to report the test in the end. Okay, so in this expression, I do get cancellation of these, and I am left with, at this point, you could divide this over or you can distribute it. I think I'll just divide it over. And because I'm dividing by a negative, this inequality is going to flip. And what I'm left with, keeping track of all these positives and negatives, I have on the left side 2 mu1 sum of the wi minus 3 mu1 squared is greater than or equal to some constant k2, which happens to be -4 times the old constant. And the inequality has flipped because I multiplied or divided both sides by a negative. And now, still in my quest to isolate the w's, I am just going to move this to the other side. Just going to add it over there. And I get 2 mu1 sum of the wi greater than or equal to some k3. And finally, I'm going to divide by this. Now we are given that mu1 is greater than 0. So when dividing by that, I'm not going to flip anything. And we get the sum of the wi greater than or equal to some k4. And let me put the I range on there. So the best test of size alpha for the simple versus simple case, according to Neiman and Pearson, is going to have this form. We're going to reject the null hypothesis in favor of the alternative if the sum of the w's is greater than or equal to some k4. And for my rejection rule, I want to give everything nice and random and uppercase at this point. And k4 is just a constant to be determined. And to determine that constant, we need to use alpha. So alpha is the probability of making a type 1 error. In general, it is the maximum probability of making a type 1 error, but you only need to worry about the maximum if you have a composite null hypothesis, because this is supposed to be the maximum over all mu in the, actually, let me not write that yet. Let me be a little more general here. It's going to be the maximum probability of rejecting the null hypothesis when it's true. And when it's true, I'm going to change that to say when the parameter is mu. And then in the maximum, I'm going to take care of the null hypothesis being true. So this is the maximum over all mu equals 0. So there's only one point there to maximize over, and it's fine if you never even brought the maximum in. But this is going to be the maximum over all mu equal to 0 of the probability we reject the null hypothesis, and that means that the sum as I goes from 1 to 3 of the Wi is greater than or equal to some k4 to be determined when the parameter is mu. And so because I'm maximizing over all mu equaling 0, there's only one value there. So this is the probability, the sum as I goes from 1 to 3 of Wi greater than or equal to k4 when mu is 0. Okay, so now we want to compute this probability. On the left over here, we have a sum of 3 independent and identically distributed normals, and that is again normal. And the mean for this, the expected value for W1 plus W2 plus W3, you can run the expected value across and you get 3 expectations. And in this case, under the assumption that mu, well, in general, this is going to be mu, or 3 mu, but that's going to be 0 when mu is 0. And then the variance, if you wanted to first turn this into like a W bar, you could do that. I'm not doing that here, but the variance of W1 plus W2 plus W3, because they're independent, this is the variance of W1 plus the variance of W2 plus the variance of W3. And I don't think I ever wrote down, let me just double check here. Yeah, I never wrote down at this point the variance of the sum, but each one has variance 2, and we're getting to add those variances together. So we get a total of 2 plus 2 plus 2, so 6. Okay, so under the assumption that mu is 0, this has this normal distribution, and we're ready to standardize it and turn it into a z. So on the left side, I'll take the random variables minus the mean. So that is going to be, I'm just sort of at a loss for notation here. Like I could write the mean of the sum, or usually we do it symbolically on the left side of the inequality and then numerically on the right. But because I don't want to come up with symbols for those things, I just think I'll do it numerically on both sides of this inequality. So I'm going to subtract 0 and divide by the square root of 6. Now, the way I'm doing it, I never made a W bar. So there's no like 1 over the square root of n part in there. And on the right side, greater than or equal to k4 minus 0 over the square root of 6 when mu equals 0. Now, this random variable is a standard normal, so we'll call it z. And this is greater than or equal to k4 over the square root of 6. And I have kind of used up this information because if mu wasn't equal to 0, then this would not be properly centered and wouldn't be a standard normal. But it is, and the standard normal distribution does not depend on any unknown parameters. So I've used up this information by going from here to here, where z is a standard normal. Okay, let's pull it all together. I've got alpha is the probability that z is greater than or equal to k4 over the square root of 6. And are we given an alpha in this problem? No, it's just a generic alpha. So for the standard normal distribution, I want to be above, so that's way too fat of a tail there, but I want to be above some number with probability alpha. And if you've taken a class with me, we usually call this critical value z sub alpha to be the number that cuts off alpha area to the right. Some people use a z sub alpha for the number that cuts off alpha area to the left. And if you want to do that, great, but draw the picture so that the grader knows what you're doing, what this is notation for. And if you don't want to use any of this notation, you might just call it like C or something, as long as you draw the picture and maybe say where C is a number that cuts off area alpha to the right. And so this has to be equal to Z sub alpha. So we've got that K4 over the square root of 6 is equal to Z sub alpha. And this means that K4 is equal to the square root of 6 times Z sub alpha. And so let's pull it all back together. The rule is going to be to reject the null hypothesis in favor of the alternative if the sum as I goes from 1 to 3 of the WI's is greater than or equal to the square root of 6 times the critical value Z sub alpha. And we are done with part A. Okay, so before doing part B, which is the tricky part, I want to jump to part C because part C is just an extension of part A. So in part C, remember this test for part A was mu equals 0 versus mu equals a fixed mu1, where mu1 is greater than 0. And in part C, we want to find a uniformly most powerful test for this null hypothesis versus that mu is greater than 0. And the way you do that is you first fix a value for the alternate hypothesis where that value is fixed to be greater than 0. And then you find the best test. And then you say, look, here's my best test. And it doesn't depend on the particular value of mu1 that was chosen. The direction of the test does depend on mu1 being greater than 0. So this test here is going to work for all mu1s greater than 0. So part C, the test doesn't depend on the particular mu1 as long as it's greater than 0. So it's uniformly most powerful or best or most powerful for any mu1 that we choose in this region. So it is the uniformly most powerful test, or I just say UMP, for the null hypothesis that mu is 0 versus the alternative that mu is greater than 0. And so we're done with part C. And now I have to go back and pick up part B. In part B, we're going to include W4 in the problem. And that means that these are no longer IID. These are IID, but this one is not independent of the others, and it is actually not identically distributed. So we're going to need to use the multivariate normal distribution. And before writing that down, I just want to write out the PDF for NIID normals, because this, you don't have to do this, obviously, but this helps me remember the PDF for the multivariate normal. So for these IID normal with mean mu and variance sigma squared, the joint PDF is gotten by multiplying the individual PDFs, and we get 2 pi sigma squared to the minus n over 2 e to the minus 1 over 2 sigma squared, the sum of the xi minus the mu all squared. Now, for the multivariate normal distribution, there is a mean vector mu and a variance covariance matrix V. And for describing the multivariate normal distribution, it's preferable and easiest to keep everything in terms of a column vector. So x here is going to be n by 1, and mu is going to be n by 1, and v is going to be n by n. So mu is, just for the purpose of space, I'm going to write it as a row vector transpose, but this is the mean for all of these random variables individually. transpose. And then V is, as I said before, an n by n matrix. And the ijth entry is the covariance between xi and xj. Okay, so let's write this joint PDF out in the case of W1, W2, W3, and W4. So here we have n equals 4, and mu is going to be the vector of means for W1, W2, W3, and W4. So we already know the expected value for W1, 2, and 3. This comes from the expected value of x1 plus y1, and you run the expectation across because it's a nice linear operator. And the expected value or mean for the x's, they were mu's, and for the y's, they were zeros, so we get mu. And we're going to get that for W1, W2, and W3. And the expected value for W4, this is the expected value of x1 plus x2. And when you run that expectation across, you get the mean mu for the x1, and you also get mu for the mean of x2, so you get 2 mu. So there is the mean vector, and V is going to be a 4 by 4 matrix. And the ijth entry is going to be the covariance between Wi and Wj. So let's look at the 1, 1 entry. The covariance between W1 and W1 is the variance for W1. And we already know this, but in case you forgot, this is the variance of x1 plus y1. And because the x's and the y's are independent, this is the variance of x1 plus the variance of y1. And both of these had variance 1. That's the original setup of the problem. So we do get a 2 in the 1, 1 entry of this matrix. Now, W1 is independent of W2, so the covariance, they're uncorrelated or have a correlation or equivalently a covariance of 0. I'm going to get a 0 there. And the same thing for W1 and W3. Those are independent, and they have a correlation and hence a covariance of 0. So this last entry is going to be a little different. Let's look at the covariance between W1 and W4. This is the covariance between x1 plus y1 and x1 plus x2. And for a covariance involving sums like this, you can distribute, kind of like FOIL this out. You get the covariance of x1 with x1 plus the covariance of x1 with x2 plus the covariance of y1 and x1 plus the covariance of y1 and x2. So x1 and x2 in particular, they are independent and they have a covariance of 0, so that's going to 0 out. Y1 is independent of x1, so these guys have a covariance of 0. Same thing for y1 and x2. Covariance is 0. And the only thing we're left with is the first term, the covariance between x1 and x1, which is the variance for x1, and that is 1. So I'm going to put a 1 in the 1, 4 entry of the matrix. Okay, the second row is similar. I mean, things are mixed up a little bit. So W2 and W1 are independent. They have a covariance of 0. W2 and W2, that's just the variance for W2, which is the covariance between W2 and W2. It is the exact same calculation here, and we get a 2. W2 is, oops, sorry about that. W2 is independent of W3, so the covariance there is 0. And then W2 and W4. So that would be like going to this lower calculation here and replacing this 1 with a 2. And so this x1 down here is going to be a 2, and this is going to be a 2 and a 2. You can follow that through. And only one term will survive. and that will be the covariance between x2 and x2, which is the variance of x2, which is 1. Okay, W3, things get a little bit different because W3 is independent of W1 and W2, and by construction of these W's, it's also independent of W4. So the covariance between W3 and W1 is 0. The covariance between W3 and W2 is 0. The variance of W3 is the same variance we computed for W1 and W2, and that was 2. And the covariance between W3 and W4, so if you look at those in particular, W3 was X3 plus Y3, and W4 was X1 plus X2. So there's no overlap in indices, and those are independent random variables with a covariance of 0. And if you want to keep reasoning your way through this as a check to make sure you're doing things right, then go ahead. But I'm not going to do it. I'm just going to fill out this matrix. A variance-covariance matrix is always symmetric. So the 4-1 entry is the same thing as the 1-4 entry, which is 1. The 4-2 entry is the same thing as the 2-4 entry, which is 1. The 4-3 entry is the same thing as the 3-4 entry, and that is 0. And I don't have a symmetric point here. So the 4-4 entry, is the covariance between W4 and W4. And that is the variance of W4. And that is the variance of X1 plus X2. And those are independent. So you do get to run the variance through. And each of those had variance 1. So we get to yet again. Okay, so I am just going to summarize the joint PDF here because we're going to need it. We're trying to find a best or most powerful test, and we're going to use the Neiman Pearson lemma. And I think first I'll use the full notation, which is to have a mean vector and the variance covariance matrix. So this is 2 pi to the minus n over 2, and n is 4. And then the determinant of v inverted and square rooted, so to the negative 1/2, e to the minus 1/2, w minus mu transpose v inverse w minus mu. Now that I write this, I realize that I forgot to do this up front, which was the whole reason for me writing down the joint PDF for the IID normals. It was to compare this to that. And I have forgotten that 3 times now. I'm not refilming this video again. So you can see the sort of IID normals there, right? Because that usually has a 2 pi sigma squared to the minus n over 2. This comes out on its own, and it is in the denominator, so it's negative, and it is a square root, but you don't have an n when you write it with the variance covariance matrix because that's already built into the matrix, which is n by n. And this is the way of getting the sum of the squares. And if you are not certain whether to put the transpose here or here, note that this function is scalar valued. So this needs to be a 1 by 1. And it is, because W is 4 by 1, and mu is 4 by 1, and V is 4 by 4. Okay, so let's look at the Neiman-Pearson lemma. Here we want to make a ratio of the joint PDF. It is a likelihood ratio, and I call it lambda. And I am going to change the notation here. Because the V is constant in both of them, I'm just going to think of it as constant and only talk about this joint PDF here. You don't have to do this, but I get a lambda of W and then the 0 vector, and that is the mu, 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 2 mu transpose with mu equals 0 plugged in. And then I'm going to have a mu vector, which is going to be this mu, 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 2 mu, with mu equals mu1 plugged in. So this is supposed to be for the null hypothesis, and this is for the alternate hypothesis. I don't know, maybe you want to call that mu1 vector. We could do that. Okay, so this is the PDF for the W's with the 0 vector plugged in over the PDF for the W's with the mu1 vector plugged in, which again is this vector, but with mu1s in place of mu. So looking at the joint PDF, we can see that the 2 pi stuff is going to cancel, and also this determinant is going to cancel. So what is left is e to the minus 1/2. And then in the numerator, we have W transpose V inverse W. In the denominator, we have W minus mu1. Sorry, I'm calling it mu1 now. W minus mu1 transpose V inverse W minus mu1. And we're going to set that for Neiman Pearson. We're going to set that less than or equal to some constant K to be determined. And before we try determining any of these constants, we usually simplify what we can and try to move as much as we can to the right-hand side while keeping everything involving W's on the left-hand side. Let's go ahead and take the log of both sides. So we're going to be left with this, less than or equal to a constant K1. And also, I want to divide by the negative 1/2, which is going to flip the inequality and give me another constant K2. Now, it really doesn't matter that I've numbered all of those. So this is going to be, this line here is equivalent to W transpose V inverse W minus W minus mu1 vector transpose V inverse W minus mu1. Looks like I have a prime up above. Let me fix that. Vector. And this is going to be greater than or equal to K1, or maybe K2 or K3 if you really kept track of each little move you made in simplifying the line above. Okay, so this looks bad, but if you remember part A, it kind of looks similar. And in part A, we squared out the thing that was squared and ran the sum through, and then we got some cancellation from this term. And so let's try that here. This vector, I can put the transpose on each of these, and then I can kind of multiply this stuff out. So I've got the W transpose V inverse W minus W transpose V inverse W, and that came from this transposed and this and this, and then plus, so I've got this negative out here that I'm dealing with as well, plus W transpose V inverse mu1 plus mu1 transpose V inverse W minus mu1 transpose V inverse mu1. And that is greater than or equal to K1. I haven't actually, moved anything around. I just expanded out the left-hand side. So here is a constant in the W's, and it can go to the other side. So just add it over there, and we get a new constant K2. Also, this is going to cancel with this. So when you do this, you are left with W transpose V inverse mu1 vector plus mu1 vector transpose V inverse W. And this is greater than or equal to a K2, where K2 is K1 plus this term. This looks bad. The next thing we would do at this point is to write down the type 1 error probability with alpha and try to solve for K2. And if you're not well versed in multivariate normal, then it looks bad. But it's really not that bad because this W transpose is 1/4, V inverse is 4/4, and mu is 4/1, making this entire thing 1/1 or a scalar. this thing over here is the transpose of this thing. So it's a scalar transpose. It's the same exact scalar. And so this is equivalent to 2 times one of these. I have to choose one. I'm going to go with this one. Mu1 transpose V inverse W greater than or equal to K2. And this is a scalar. So we are down to one-dimensional computations, as ugly as it might seem. You might also move the 2 to the other side, and that might be it. But if you continue, your rejection rule will involve the mu1. Let me look back at the problem. Are we getting a best test? So we're not trying to get a uniformly most powerful test. We don't want to really see that mu1 in the statistic, especially if we're going for a uniformly most powerful test, which we are not. But check this out. This vector is, there's a mu, which is a scalar, and then there is a it's a mu1, and then there's a 1, 1, 1, 2 transpose. And I can move this to the other side and this, and then I'm still left with this, which is a scalar. So, yeah, we were given that this mu1 was greater than 0. So when we move it, the inequality is not going to flip. So we have like some A transpose W greater than or equal to some K3, where A transpose is equal to this 1, 1, 1, 2 transpose times V inverse. So the form of our test is going to be to reject the null hypothesis in favor of the alternative if A transpose W is greater than or equal to K3. And the A transpose is completely known to us because we did write down the matrix V, although we haven't inverted it. I'm still hoping we can get away with not doing that. Okay, so now we want to find K3. Here's where alpha comes in. Alpha is the probability of making a type 1 error. You don't need to worry about a maximum or a supremum because we do have a simple null hypothesis. So this is the probability. We reject the null hypothesis when it's true. And rejection for us means that A transpose, I need to make sure these are capitals now. Sorry, I didn't do that. But we want our random variables in our rejection rule. And so I'm going to copy that down here. We want to reject when A transpose W is greater than or equal to K3. And when the null hypothesis is true, means that mu equals 0. And then what you have is a scalar normal. And it looks like the sum AI WI as I goes from 1 to 4. And so you should move to that if you're uncomfortable with the vector operations. I am going to keep the vector. So this is a scalar normal, and the expected value of A transpose W. This one I will write out as that sum. So when you run the sum through and you pull the AIs out, you're going to end up with the expected value of 0. This is under the assumption the null hypothesis is true. Yeah, so the expected value of like W1 and W2 and W3 was mu, and that's 0 under this assumption. And the expected value of W4 was 2 mu, and that's 0 under this assumption. So you'll get a 0. The variance of A transpose W, this is a scalar, and the long way would be to plug this in, and they're not IID, so you can't run the variance through. So then I would put the covariance of this with itself and start like multiplying that out. But I'm going to go ahead and use the vector matrix version of pulling a constant out. Now, if this was just a scalar A, it would come out squared. And what happens with the vector is it comes out, and then on the other side, it comes out transposed. And just as a quick check, this is 1 by 4, this is 4 by 4, this is 4 by 1. So we did that in the right way. And this is A transpose V A. And what was my A? My A transpose looks like this. So A transpose is 1, 1, 1, 2, transpose V inverse, and then we get the V, and then this part, which I think I'm just going to write as, I'm going to write as A again. So we get cancellation here, and this is 1, 1, 1, 2, transpose A. A is 1, 1, 1, 2, V inverse. Yeah. Now the inverse gets transposed as well, but the V is a symmetric matrix, and V inverse is going to be symmetric. The test is to reject when this happens, and we can standardize this into a standard normal. Under the null hypothesis, we would subtract the mean of 0, and then we would divide by the variance here. So let me try to at least clean that up. We have alpha is the probability of A transpose W greater than or equal to K3 when mu is 0. And again, this is a scalar, so I can subtract the mean of 0 and divide by the square root of the, I'm just going to write the variance of A transpose W greater than or equal to K3 over the square root of the variance of A transpose W when mu equals 0. So now this is a univariate standard normal. And that W, I've lost my vector on that. So let me put those in. And once you've turned it into a Z, the distribution of Z does not depend on the unknown mu. So you don't need to know mu anymore. So we've kind of used up that information. And because this is set equal to alpha, we know that K3 over the square root of the variance of A transpose W is going to be the critical value Z sub alpha, or whatever you call it, as long as you've defined it or drawn a picture. And so we can solve for K3. So the final test is to reject the null hypothesis if A transpose W is greater than or equal to this variance times Z sub alpha. Yeah, and that's it. I mean, I'm a little lazy. I'm not writing the in favor of, but this is the statistic you would look at. And note that it doesn't actually depend on the mu1 chosen. Now, in problem B, we were not asked for a uniformly most powerful test, just a best or most powerful test for the simple versus simple case. So we are done. And I guess that's what I would do if this was on the prelim. I would leave it like this, and that is going to be in terms of V inverse. And maybe if you had a lot of extra time at the end, after you finished everything, you could try to invert that V by hand, but I certainly wouldn't waste time on it while other problems needed to be done. See you in the next one.